Hypothalamus artificial intelligence, HI. Digital transformation with artificial intelligence and real-time optimization. At HI, we take mathematical optimization to the next level with OPTEX-GAMS, our platform designed especially for GAMS users. As GAMS business partners, HI offers training courses in GAMS, from basic to advanced level. These courses can be adapted to the needs of each industry, providing practical tools to apply mathematical optimization in different sectors. This lecture deals with the topic of chaining optimization GAMS problems, one of the main objectives of which is to accelerate the execution of the solution of large problems. As will be seen through the talk, there are many alternatives. And all of them are linked to the modeler's knowledge of GAMS. Conference edited by Dr. Jesús Velasquez-Bermudez, Chief Scientific Officer of HI. Chaining optimization problems. Speed up the solution time. Construction of mathematical models in GAMS. The mathematical modeling process can be defined based on the following steps. Observe and study the real world, algebraic modeling of the real world design of data model, from the industrial data information system, matrix generation, union of the algebraic model and the data model to obtain a numerical model, solve the numerical model, using a solver according to the format of the problem, and recovery of results so that they are useful for decision makers. There are multiple commercial and free license solvers, which can solve the problem. In principle, all solvers solve the problem, but the difference between them is the time and memory for solving the problem. The modeler should select the solver considering technical and economic impacts. The most used solvers are shown in the figure. Between groups of comparable solvers, for example, commercial, Plex, Nitro, Express, Gorobi and Lindo, and non-commercial, Coin or LPs, GLPK, there is no solver that is dominant. As the size of numerical models grows, commercial solvers are dominant. The ideal solver selection is to test it when the algebraic model is available and to rely on an objective study of which is the best solution. In modern low-level languages, such as R, Python, Java, Julia. To facilitate development, mainly the process of generating arrays, a library of optimization objects must be linked. In modern low-level languages, such as R, Python, Java, Julia. To facilitate development, mainly the process of generating arrays, a library of optimization objects must be linked. The alternative is to use fourth-generation computer languages, oriented to algebraic modeling, and connect the algorithms directly with the solvers. Examples: GAMS, IBM OPL, AMPL, Mosel Lingo, AIMS, and GMPL. HI prefers to use this type of language because shorter programs, with fewer lines, less programming time, and unified platform for multiple specialized services. In general, there are two types of solvers: outer point algorithms or simplex type, and interior point algorithms or barrier type, or primal dual type. The simplex method divides primal variables into basic, denoted as XB, and non-basic, denoted as XN. The non-basic variables, XN, are associated with the submatrix N, and the basic variables, XB, with the submatrix B, which is called the basic matrix, and define a feasible basic solution. At any stage of the algorithm, the basic variables are expressed as a function of the non-basic variables, which are fixed in one of their bounds, higher or lower. The simplex algorithm performs pivot operations, each of which provides an improved feasible basic solution, in terms of the objective function. The choice of pivot element in each step is largely determined by the requirement that this pivot enhance the solution. A commercial simplex algorithm is much more complicated than this simple version. This conception of basic and non-basic variables extends to nonlinear algorithms, such as the generalized reduced gradient, GRG. Below is a visual presentation of the displacement of the two types of algorithms. The step of going from the starting point, whatever it may be, is traditionally referred to as crash or presolve. In the case of outer point algorithms, the crash solution point must be a feasible basic point, becoming the basic feasible starting point of the algorithm. From this point on, the optimization itself begins, which should lead to the optimal solution. Since it is an external point algorithm, optimization is done by visiting the extreme points, basic solutions, of the constraint set. Since the only way to get to the optimal point is by visiting extremes points, as the endpoints increase, the algorithms will face time and memory issues. The solution obtained is a basic feasible optimal solution, since a primal solution complies with the primal feasibility zone, and the dual solution, with the dual feasibility zone. The steps of an outer point algorithm to solve the optimization problem are: crash/presolve, compaction of the matrix to its minimum expression. Removal of constraints that are definitions. FOSS-AI, feasibility search. FOSS-A2, optimality search. Crossover, search for an optimal feasible basic solution. Optional if dual information is not required. Necessary for a re-optimization. Recovery of the solution in the original space. In the case of interior point algorithms, the crash solution point must be any feasible point, becoming the starting point of the algorithm. This phase of optimization is not necessary if the modeler do not want to perform it. The interior point algorithms cross through the primal feasibility zone, establishing a barrier that through penalties ignores the constraints of the problem. When the barrier is removed, the optimal solution to the problem is obtained that is called the interior feasible optimal solution. At first this type of algorithm ignores the constraints, so it is insensitive to their number. As it gets closer to the optimal solution, the active constraints come to guide the search. For very large problems, the behavior of this type of algorithm does not increase its complexity as a function of size, it is an advantage over outer algorithms. On certain occasions, mainly in cyclical problems, the solution of an interior point algorithm is not a basic feasible solution. This is because at the end of each calculation numbers are generated that will always give approximate solutions. If the results of an optimization process will be used again, a basic feasible optimal solution is needed. The process for traveling to the basic optimal solution is called crossover. The steps of an inner algorithm, the process to solve the optimization problem are: search for feasibility and optimality, based on a primal dual approach. Crossover, search for an optimal feasible basic solution. Optional if dual information is not required. Necessary for a re-optimization. Recovery of the solution in the original space. Chaining different types of problems. This topic is of great interest considering that the mathematical programming in the Industry 4.0 must be based on parallel optimization, which implies the chaining of multiple problems, using the concept of partition and decomposition of large problems. The types of problem chaining can be classified into: first, large-scale optimization methodologies, like Bender's theory, Lagrangian relaxation, Dantzig-Wolff, and cross-decomposition, and their variations. The standard loop implementation is shown in the image. The implementation of large-scale optimization methodologies implies that solution of the original problem is obtained solving multiple sequential family of problems. Between optimizations, a database of cutting planes is formed, to be used in the next iteration of a coordinator problem. This database must be cached for maximum speed, but it may be in RAM, if the speed of the optimization process allows it. Second, convex and non-convex hulls, like Pareto curves for multi-criteria goals, optimal solution functions, and cost of deviations of optimal solutions. Other case is Pareto curves for multi-criteria goals. In this case, it is necessary to build a multidimensional matrix that relates the goals to each other, in terms of the growth of one goal with respect to the others. The image shows a Pareto curve expected income versus risk assumed. The process of constructing the Pareto curve involves: define the extreme points of the curve, green dots. This is not necessary, but it can be convenient, and evaluate the inside points of the curve, red dots. This involves the sequential solution of several problems of the same family. This process can take advantage of the parametric growth of multi-criteria objectives. Other case is the use of convex hulls or non-convex hulls to represent complicated parts of an optimization problem. The example comes from the use of convex hulls in the real-time optimization of crude oil pumping and transportation. In this case, pumping stations complicate the problem as they are associated with nonlinear polynomial relationships, to represent energy losses, chaotic behaviors, discontinuities, associated with pumps with minimum flow, and binary variables that activate the pumps of the station. The idea is to replace the problem associated with a pumping station with a non-convex hull that represents the optimal solution for the pumping station. Convex or non-convex hulls are represented by a multidimensional grid of control variables of the represented object. In the case of a pumping station, the control variables are pressure and flow. There will be a grid for each child variable that the modeler wants to include in the model, for example the energy. Each point of the grid represents the optimal operating conditions, when the station is worked complying with the control variables. In the image there are two pumping configurations that depend on the value of two scenarios of the control variables. Building the grid may be in an offline process, which must be solved for n tuple of control variables of the object, the pumping station. This process, which may seem enormous, is usually very fast, because the sub-problems of the entities correspond to small-scale problems. The equations that represent the hull correspond to an interpolation in two dimensions. Due to the non-convexity, binary variables are required for their correct representation. More detailed information of this case can be found in the Chapter 4 Oil Pipelines Real-Time Optimization, book and edition by Velasquez-Bermudez. The process to follow is: extract the object or entity subproblem from the original problem. Then, in isolation, construct the hull grids for each tuple of the control variables and store the results in a database. To enter the hull grids into the original problem, the modeler must use the interpolation equations. And third, special models, like data envelopment analysis, cross-validation, and statistical models. DEA, data envelopment analysis, will be presented in detail in a later section. Re-optimization of chains of problems. Below is presented the fundamentals of re-optimization. The analysis is performed for the simplest case that can be considered, that is a linear problem in which the matrix of constraints remains constant for all iterations, denoted by A in red. And changes only are permitted in the vectors of bounds, U, the vector of costs, C, and the vector of resources, B. All vector are in blue. The subscript I indicates the sequence of the problem PLI to which the problem PLI plus 1 follows. The vectorial variable xk is the primal optimal solution, and pi k the dual optimal solution. The analysis is based on determining how the feasibility zone of the original problem changes, depending on the change of a component of one of the dynamic vectors. The matrix formulation of the problems, primal, blue, and dual, red, is presented. Let's assume that we are working with two basic algorithms. Primal simplex, working in the primal feasibility zone, fulfilling the feasibility conditions of the problem, seeking to meet the optimality conditions, and dual simplex, working in the dual feasibility zone, fulfilling the optimality conditions, seeking to meet the feasibility conditions. In this first case, an optimal feasible solution is available, and the feasibility zone is modified in such a way that the new problem covers the previous one. The re-optimization must use the primal simplex algorithm. In this case, an optimal feasible solution is available, and the feasibility zone is modified in such a way that in the new problem the dual feasible zone covers the previous dual feasible zone. The re-optimization must use the dual simplex algorithm. The algorithms considered in the IBM C-Plex optimization library, more than 5 years ago, are shown in the image. Important the notation about the use of these algorithms. Barrier optimizers. They can scan multiple threads simultaneously, and they cannot start from an advanced base and therefore have limited application in processes of multiple cycles of similar problems, as is the case of the MIP solution using branch and bound. It should be noted that re-optimization with an exterior algorithm, like simplex, is faster when starting from previous basis. The table shows the algorithms available in IBM CPlex for linear programming. The primal simplex, dual simplex and network simplex algorithms can be used in the re-optimization process. Indoor point algorithms such as barrier, sifting, and concurrent barrier cannot be used in re-optimization. Chaining optimization problems using GAMS GUS and GAMS SolveLink. Speed up the solution time. The following sessions concentrate on the use of GAMS to handle the theory and the cases considered in the previous sections. In summary, there are two options in GAMS, SolveLink and GUS. Alexander Merouse, Richard Price, and Gary Kuchar founded the GAMS Development Corporation in Washington, D.C. in 1987. Merouse and Franz Nelissen founded GAMS Software GmbH in 1995. Michael Busiek is the actual CEO of GAMS Incorporated. To date, HI and GAMS have strong alliance in decision-making artificial intelligence. GAMS SolveLink. The screenshot shows the SolveLink options available in GAMS. These options may be grouped into three sets. Group 1. Model instance and entire GAMS state saved to scratch directory, GAMS exits. Chain, script equals 0. Model instance and entire GAMS state saved to scratch directory, GAMS exits, and vacates memory, and the solver script is called. After the solver terminates, GAMS restarts from the saved state and continues to executing. Group 2. Model instance saved to scratch directory. The solver is called from a shell while GAMS remains open. Call, script equals 1. Model instance saved to scratch directory. The solver is called from a shell while GAMS remains open. Call module equals 2. Model instance saved to scratch directory. The solver is called with a spawn, if possible, or a shell, if spawn is not possible, while GAMS remains open. Async grid equals 3. Model instance saved to scratch directory. The solver starts the solution and GAMS continues in a grid computing environment. Async simulate equals 4. Model instance saved to scratch directory. The solver starts the solution and GAMS waits for the solver to come back but uses same submission process as 3, test mode. Group 3. The model instance is passed to the solver in memory. Load, library equals 5. The model instance is passed to the solver in memory, without use of temporary files. Load library async equals 6. The model instance is passed to the solver in memory. The solver starts the solution and GAMS continues in a grid computing environment. Load library async simulate equals 7. The model instance is passed to the solver in memory. The solver starts the solution and GAMS waits for the solver to come back but uses same submission process as 6, test mode. The image presents the most used options in the three groups. The information should be understood as informative, but it is the modeler who must analyze the best option to use, which may depend on the problem. SolveLink option controls GAMS functions when linked to the solver. The following SolveLink options are used in this case. Chain, script implies GAMS vacates memory, plus maximum memory available to solver, plus protection against solver failure, minus swap to disk. Call script and or call module imply GAMS stays live, plus protection against solver failure, plus no swap of GAMS database, minus file-based model communication. And load library implies solver DLL and GAMS process, plus fast memory-based communications, minus not supported by all solvers. GAMS, gather update solve scatter, GUSS. The article. GUS, solving collections of data-related models within GAMS. It is a good support for learning about GUS. GUS works on the concept of scenarios and generates the model only once and updates the algebraic model by keeping the model hot in memory. The diagram presents the default loop that GAMS performs, which implies that the process of generating arrays and bootstrapping is done on each loop. The GUS loop process is simpler because the matrix generation process, and the bootstrapping are performed only once. Because no changes to the matrix are allowed, it remains constant, and only the scenario data is updated in each cycle, which can be cached. GUS presents a representation of a model instance that provides advantages from both the operator with the database approach and the model as object approach, at the cost of some functional limitations. GUS specifies possible modifiers in advance and only allows changes to the named parameters that appear in the equations and to the lower and upper limits used in the model definition. However, updating the model parameters goes far beyond updating the coefficients of the constraint matrix, the objective function, or the right side of an equation, as is possible in other modeling systems. A change in the coefficient of the constraint matrix is the result of evaluating an expression. Model sets cannot be updated, which means that the model dimension cannot be changed, that is, rows and columns cannot be added or removed in the array. All desired input and output updates are defined in the so-called GUS dictionary before the solver statement. GUS is not limited to LP, it can be applied to all existing model types within the GAMS environment. All GUS functionality is maintained, although some features, such as more complex upgrade schemes, require caution when assigning scenarios to jobs. GUS was developed particularly to solve many scenarios of the same model. This case is very frequent in the real world. Its utility has been demonstrated on several example applications and has shown significant improvements in the speed of processing collections of models. Busiek et al. 2011 report a speedup of factor 5 compared to a traditional GAMS implementation and less than factor 2 compared to the faster, but solver-dependent, IBM Plex Concert technology. In addition to a modifiable model instance, GUS handles the input and output of data from the scenario. All scenario data must be known prior to GUS processing. Therefore, data updates from dynamic scenarios that depend on the solution of a previous scenario are not possible. GUS communicates the changes between the current model instance and the ones stored in the solver only for those solvers that provide an API to manipulate a model instance inside them. Examples are IBM Cplex, Gorobi and Express. This reduces the amount of data communicated to the solver and, in the case of an LP model, allows the solver to restart from an advanced basis and its factorization. The standard loop implementation is shown in the image. The implementation of GUS involves altering the standard loop by introducing two parts, related to the adjustment of the GUS input and GUS output processes. These variations mean that within loops you must not read parameters from an external environment, such as the database. Parts of a GAMS program oriented to GUS processing have been introduced in the image. The GAMS code displays the instruction set of the GUS interface. The table shows the GUS instruction set. GUS control options set. Create a set with the names of the store metrics, and create a storage parameter indexed over the scenario set and metric set, and OPTEX-GAMS, objective function value model stat, result of the solution of the problem, optimal, locally optimal, infeasible, and others, solve stat, result of the execution of the problem, full, system error, license limitation, and others. Among others. Look at the example in the image. GUS control options set. Create a set with the names of the store metrics, and create a storage parameter indexed over the scenario set and metric set, and OPTEX-GAMS, objective function value model stat, result of the solution of the problem, optimal, locally optimal, infeasible, and others, solve stat, result of the execution of the problem, full, system error, license limitation, and others. Among others. Look at the example in the image. Log option 0 moderate report, default, 1 minimum report, and 2 detailed report. Update, type, rebuild mode for subsequent cases 0 rebuilds the model from scratch, default, 1 reconstruct the model from a base case, and 2 reconstructs the model from the last solved case. Restart, type, follow-up cases initialization mode 0 reinitializes the model from the last case resolved, default, solution, 1 reinitializes the model from the solution to a base case, and 2 initialize the model from scratch. GUS and GAMS grid facility can be used in tandem to realize the combined benefit of both approaches, representing a natural extension of GUS's capabilities. The GAMS grid computing facility allows the user to take advantage of multiple CPUs and distributed computing environments, and the SolveLink feature enables this. The process is then divided into two parts. A send loop generates and sends separate model instances to the solver. A job ID is created for each submitted model and can be used to get information about its status, for example, whether it is still running or has already ended, and a collection loop retrieves previously submitted instances, as soon as a solution is available, by accessing the corresponding job ID. The constraints discussed above remain unchanged when using GUS in a grid environment. The same dictionary can be used, with the key difference being to specify the use of the grid computing facility via the SolveLink function. The constraints discussed above remain unchanged when using GUS in a grid environment. The same dictionary can be used, with the key difference being to specify the use of the grid computing facility via the SolveLink function. Therefore, the application of network-enabled GUS is straightforward for experienced users with both GUS and grid computing facility knowledge. The GUS Grid GMS program is related to the use of GUS in distributed computing. Using a multi-core computer, or a grid of computers, digitized information for training can be found on the GAMS website. Benchmarks between GAMS GUS and GAMS SolveLink. The reference points were reported by GAMS. They are presented briefly identifying the case and reporting the time spent on each option. HY has included a column that indicates how many times an option is slower than the fastest, which is associated with the value of 1. All cases follow the same format. The first case is case, transport program solves 550 times with IBM Cplex. GUS performance, 1. SolveLink load library, 2.59. SolveLink call module, 6.63. SolveLink default, chain script, 27.29. The difference between using GUS and the GAMS per default option is 1 to 27 times faster. It is a non-negligible value, since it implies that the effort made in learning GUS makes feasible to perform in 1 hour, work that without additional knowledge in GAMS would be solved in 27 hours. What do you think? Case, stochastic model with 100 scenarios, 3,838 models. GUS performance, 1 SolveLink load library, 1.77 SolveLink chain script, 3207. Case, stochastic model with 68 small models. Its objective is to show the cost over time of the GAMS activities. The results are displayed in such a way that the time of deleting the previous activity is determined. The first indicator presents the fastest option. Communicate with solver through memory, 0.6 seconds, disposal cost, 4.3 seconds, GAMS stays in memory, 4.9, disposal cost, 4.2. Minimizing listing file size, 9.1. Disposal cost, 1.3. SolveLink default, 10.4. Disposal cost, 0. Case, Data Envelopment Analysis, DEA. Data Envelopment Analysis, DEA, is a data-oriented approach for evaluating the performance of a collection of entities called DMUs, decision-making units, which are regarded as responsible for converting inputs into outputs. DEA was developed by Charnes, Cooper and Rhodes in 1978 and has been used to estimate the efficiencies of DMUs. In various fields of application, like branches of a bank, players of a basketball team, hospitals. DEA is an efficiency measurement model, supported by linear programming techniques, which aims to evaluate the relative efficiency of different homogeneous DMUs. The application of a specific model for each DMU allows us to obtain a measure of efficiency for each of them. DEA is an extension of traditional relationship analysis for the case of multiple inputs and multiple outputs. A DMU is considered efficient if there is no other DMU that can produce a higher level of outputs, consuming the same inputs, or consume fewer inputs while maintaining the same outputs. Thus, it will be possible to distinguish in principle those units that behave efficiently from those that are not, so that efficient units define the efficient limit. To illustrate the concept, consider a simple one-in and one-out system, in which 6 DMUs are compared, each of them with the input-output pairs, L1 equals 2, 2, L2 equals 3, 5, L3 equals 6, 7, L4 equals 9, 8, L5 equals 5, 3, L6 equals 4, 1, L7 equals 10, 7. The efficient limit for this case would be represented by the graph. The efficient limit corresponds to the smallest convex envelope, convex hull, that contains all DMUs. The DMUs that remain in the envelope are efficient. In the graph it can be seen that the L5, L6 and L7 DMUs are inefficient since visually better possibilities of using the resources of these DMUs are identified, as shown in the figure. In the graph the L5, L6 and L7 DMUs are inefficient since visually better possibilities of using the resources of these DMUs are identified. The area delimited by the red lines implies a better use of the resources, inputs, used by the L5 DMU. From the output point of view, the consumption of DMU L5 is higher than required by other DMUs. From the input point of view, the production of DMU L5 is less than potential by other DMUs. The screenshot presents two parts of the DEA implementation in GAMS GUS. Program DEA GUS.GMS. The screenshot shows a table defined in the GAMS program, which is shown interpreted in a window on the right side. The case analyzes the efficiency of 20 warehouses. The table presents the result of the DEA analysis, which is elaborated, once the 20 problems have been run, one for each deposit. Case, DEA, Data Envelopment Analysis. GUS Performance, 2.53 Solve Link Load Library, 1 Solve Link Default, 15.13. This is the unique case in which the best option is a Solve Link option. The screenshot shows the directory containing the GAMS programs related to DEA. Case, SDDP, Stochastic Dual Dynamic Programming. The Stochastic Dual Dynamic Programming, SDDP, algorithm for solving multi-stochastic linear programs using nested Bender's decomposition, based on the concept of a future cost function, FCF. The algorithm works with an underestimate approximation of this FCF by iteratively adding supporting hyperplanes, Bender's cuts, and therefore improving the approximation. This implementation uses Gather Update Solve Scatter, GUSS, in GAMS, making the many related solves efficient. An implementation using traditional loops can be found at the web. This SDDP algorithm has been implemented using IBM C-Plex Concert technology. The C++ source code is available at the web. The data and core model has been provided by Vattenfall Energy Trading. Stochastic Dual Dynamic Programming, SDDP, is a widely used methodology in the optimization of the electrical systems. The GAMS program SDDP.GMS solve a multi-stage stochastic water reservoir model using SDDP. The source code may be downloaded from the web. Case, multi-stage stochastic water reservoir model solved with SDDP, with 66,320 linear problems. C++ application performance, 1, using IBM C-Plex Concert technology GUS performance, 1.87 Solve Link Load Library, 5.81 Solve Link Default, 34.30. The case shows that GUS improves the GAMS application 18.5 times, but C program improves GAMS GUS 1.87 times. The case allows us to conclude that in real-life cases not using advanced technologies can imply great mistakes, because a problem that seems not to be soluble with the default characterization of the algorithm can be solved comfortably with state-of-the-art technologies. Case, Robust Supply Chain Design. The article, Design of Resilient Supply Chains with Risk of Facility Disruption. It is the source of this case. Case, Robust Supply Chain Design 3 Distribution Centers. GUS Performance, 1 Solve Link Load Library, 1.164 Solve Link Default, 5.633. Case, Robust Supply Chain Design 9 Distribution Centers. GUS Performance, 1 solve link load library, 2.365 solve link default, no solution. This is another example in which parameterization of the use of the model allows a solution to be obtained in a finite time. Thank you for your attention.